Okay, so we're happy to have Dustin today telling us about the properties of Hamiltonian theory on surfaces.
Thank you. Yeah, thanks everyone. Lovely to be here. So I'd like to talk about, as the title says, sort of dynamic and topological aspects of Hamiltonian Floer theory on surfaces. And so just for by way of general motivation here, we can, oh goodness. Okay, no, I don't, sorry. Okay, I don't know how this is
I
gonna.
think you want to go back and forth on the arrow keys, I guess.
Back
If
and
you
forth
do,
on
like,
the.
play it pause.
Oh, I see,
it'll
I
start
see.
rolling
Okay,
it.
brilliant. Okay. So the general motivation here is basically that Floer theory is very useful. I think, you know, the past, I guess, like 40 some odd years of development of the theory sort of like shown us this, right? But okay, problem that we have is that it's often not particularly clear, like what the dynamical nature of the objects that you sort of or the invariants that you sort of compute from Hamiltonian Floer theory is. So, for instance, you know, okay. So if I give you a Floer chain, for instance, and I ask you, you know, what does it mean for it to represent the fundamental class? Okay, if you have in the Moore setting, for instance, this is very clear, right? The fundamental class is represented by the sum of the maxima, right? But okay, in Floer theory, what does that mean? Okay, pretty unclear. So maybe useful question to sort of measure the extent of our ignorance about this kind of thing, right? More broadly, what kind of dynamical behavior is measured by spectral invariants, right? If I give you a Hamiltonian and say it's like not a C2 small Hamiltonian, I ask you, what are the spectral invariants? What's the barcode of this Hamiltonian dynamical system? Generally speaking, we just don't know. Okay. Okay. Relatedly, somehow, what's the relationship between the moduli spaces used to define the Floer complex and the dynamics of the isotopy? Okay, somehow this should be, I'm wanting to contrast this again with the Morse case, where somehow, you know, we understand quite well how the moduli spaces used in Morse theory kind of help you reconstruct the structure of the function, right? Can you somehow, through understanding moduli spaces of Floer cylinders, you know, can you reconstruct something of the dynamics? Can they help you understand the dynamics somehow, right? And okay, maybe to put a finer point on that, you know, can we use Floer theory to get some sort of, you know, useful conceptual picture of conservative dynamics in the same way that Morse theory gives you kind of a useful conceptual picture of what a smooth function or a generic smooth function is like, right? And okay, I'll say a bit more on what useful conceptual picture what I mean by this, okay? And so the goal of this talk here, we're gonna sort of talk about some results going towards answering some of these questions. And I'd like to, throughout this talk, assume that we're on a surface and that surface is aspherical, okay? These results do apply to the sphere when you take into account cappings, and this is useful, but somehow that will complicate things needlessly. And I'd like to kind of get the picture clear. Although I will say just this will at one point run us into sort of like unfortunate kind of terminological problem, but I'll signal that at the moment. Okay, and just to give the central idea, so I'm going to explain sort of a few results that kind of a priori do not, they're sort of a priori don't seem to have a lot to do with each other, except what they have to do with each other is sort of the central idea behind how you prove these things. And the central idea behind how you prove these things is to sort of understand quite well what sorts of the existence of collections of index 1 cylinders in Floer continuation maps for surfaces. And this sort of, once you understand this quite well and sort of the relative topology of such cylinders, you can use this to sort of pull information around from systems that you understand to systems that you want to study, okay? Okay. And so the broad plan, so the sort of two sets of results that I kind of want to talk about are sort of this foliation theoretic picture of the Floer complex. Okay, so somehow using moduli spaces involved in defining the Floer complex to build up foliations of both the mapping torus, the associated mapping torus, and then sort of get Calvez type foliations, which I'll explain in a moment, and then some other results about kind of measuring certain a certain kind of spectral invariant. Okay, that basically comes about by characterizing certain fundamental classes that arise that can be kind of probed by PSS type maps. Okay, and then if we have time, I'll talk about some of the strategies involved in proving these things. Okay, so let me come back to this sort of, scare quoted term that I used at the beginning of sort of a useful conceptual picture, and I want to explain what I have in mind when I say a useful conceptual picture for sort of thinking about sort of, Hamiltonian dynamics on surfaces. And I want to use as a prototype of the Patrice Calvez's theory of sort of homotopically transverse foliations for surface homeomorphisms. Okay, so if you have a surface homeomorphism, Calvez sort of develops this theory that I want to sort of explain the briefest parts of. Okay, and so here are some terms that we kind of need to understand this. So a set of fixed points are going to be unlinked if you can find an isotopy, from the identity to the time one map that fixes those points throughout. Okay, the isotopy is going to be maximal if you can't find another fixed point, such that you can contract the trajectory relative to the other fixed points that are already been fixed. Okay, and a homotopically transverse foliation for a given isotopy is going to be sort of a singular foliation. So you have some fixed points that are fixed by the isotopy. You remove those from the surface, and then you foliate the surface by sort of oriented lines. Okay, and the property of being nope.
Here. Sorry, all this stuff just makes sense only as
I mean, probably you could generalize it to like codimension one sort of things, but I mean, this is only done for surfaces. I think even getting a version that like works for, say, like contact 3 manifolds would be very nice, and somehow I guess like finite energy foliations are sort of supposed to be that. And we'll see a bit of that analogy.
So can you turn this foliations into a finite energy foliation?
Yeah, we'll get there. Yeah. Well, okay, yeah.
We'll take something like a mapping tours and then take the secret.
Yeah, well, so we'll see in a moment. Yeah, you're running that. Okay. So while Rohill does that, let me sort of explain pictorially what a sort of a homotopically transverse foliation is. Thanks, Rohill, sorry.
Don't apologize to me.
Okay.
Oh man.
So
we're back.
We're good. No,
kind of
too big, or it's does it
I
fit?
think you should.
I think that's
share
on
and
me.
reshare. That will fix the sizing.
Stop share, then reshare.
Yeah.
Okay.
Never mind. Maybe just zoom out a bit.
Yeah. Okay. Okay. So, so the idea here in a picture, right? So here's a homotopically transverse foliation, right? So what you should imagine here is that you have like the negative gradient flow associated to this sort of Morse function, right? And the isotopy, sends Z to the time one map of Z, and it, runs around, and the orbit itself is not necessarily transverse to this foliation, but it can be homotoped rel endpoints, avoiding the fixed points of your isotopy to some path that is positively transverse. Okay, so somehow this is a statement about like the homotopy class of the path rel endpoints in the leaf space of the associated foliation. Yeah, this is a good point. So for Patrice, it depends on the point. we'll see that in fact, when you use Floer theory, you can get it to be independent of the pole. Okay.
Just
but,
to
yeah.
clarify the picture, the black lines are the leaves of the foliation.
Yeah.
So this is a homotopically transverse foliation for just a Morse function? Or-
Yeah, for instance, and this is maybe a good point to mention that, yeah, if you think of an autonomous Morse function, right, then the negative gradient flow lines, they are a positively transverse foliation for the flow, right? And this is sort of your prototypical example. And in fact, somehow what we'll see is these foliations that we're going to build come about by sort of pulling such foliations toward sort of a generic Hamiltonian system. Okay.
So can you make
Yeah.
these things with, say, generating functions in the two-sphere?
So on the two-sphere, this is not done. Patrice has a construction on the two torus and on annuli using generating functions.
Okay. I'm
It's
cheating. I think you told me that.
okay. Yeah. You know, it goes. You decompose into sort of like twist use that you can decompose maps into sort of compositions of twist maps. You develop. You build these things using twist maps, and you sort of iterate these. And I personally, I find the construction to be a little tricky to follow, but yeah, one can do this. One can do this. Okay. And just to give an example of a non-homotopically transverse foliation, okay, so here we have the orbit of Z goes around, and you see that the only way to homotope this rel endpoints to something that is transverse to the entire foliation would be to pass this circle over some of these singular points, right? So this foliation is not homotopically transverse for this isotopy, okay? So some basic facts about these is that any maximal isotopy admits a homotopically transverse foliation. For any, I think this should be oriented surface, but so for any oriented surface in any homeomorphism that's isotopic to the identity. Yeah.
Maximal isotopy is I think you can maximal.
That's it. A maximal isotopy is when you can choose an isotopy that has that there are no fixed points away from the yes. Okay. And somehow it's reasonably obvious that such things exist when your fixed points are isolated, but then okay, this result of Jolon and Béguin, Calvez and Leroux is applies to sort of any homeomorphism. So the fixed point sets can be much more kind of pathological here. Okay. So, and I want to say that, generally speaking, dynamicists quite like these things, and you can use homotopically transverse foliations to sort of give you a useful conceptual picture for thinking about these things and proving interesting results. So just let me just give one example of a result that I think is kind of cool. So if you have a P periodic orbit and a Q periodic orbit that sort of intersect transversely and sort of transversely relative this foliation, so the transverse intersection is somehow none of them are tangent to this foliation, then in fact one can show that the associated time one map has topological entropy, and you can bound the topological entropy from below in terms of the periods of P and Q. Okay, yeah, I mean, so these are useful things for thinking about these. There are a lot of other interesting results. One can reprove kind of various theorems of Frank's and whatnot. Sort of his characterization of entropy zero, Hamiltonian homeomorphisms on the sphere, for instance.
Is that also like surfaces with value?
I don't want to commit to that.
I think maybe like island, but also with like a stage you have something like that for anything. Am I right?
They could. I'm not sure. Yeah.
Their theory works for homeomorphisms, so you can collapse. So it will be homeomorphisms, then you can directly work with it.
Sure. Okay. And one sort of last intriguing fact I want to point out is that we have various results that can be proved by Floer theory and sort of PFH techniques, right? that it turns out like after we've proven them with sort of with Floer-theoretic techniques, Patrice has come along and given sort of proofs that use these transverse foliations. Okay, and so there's some sort of mystery as to the degree to which these theories overlap and what can be recovered in one and what can be recovered in the other. So a meta-mathematical question is like, what's the relationship between these two theories, right? And I'd like to say something toward that during this talk. Okay, so that's a taste of kind of what I mean by a useful conceptual picture for thinking about these sort of homeomorphisms, right? I mean, these sorts of transverse foliations. In fact, we're going to get kind of even nicer transverse foliations from Floer theory, okay? And so let me sort of start discussing that. So we need a few definitions. So for me, during this talk, a braid is going to be what's often called sort of a pure braid, okay? If you're familiar with sort of braid theory, okay, by which I mean it's just a collection of loops in my surface. In fact, I'll be using contractical loops, contractical in the surface, okay? And I want the strands, I want their graphs to be disjoint, okay? So they're what you think of when you think of a braid that sort of such that each strand kind of connects, has the same endpoints, okay? They're pure braids, okay? This, for instance, is not a geometric pure braid, right? Because as we can see, x2 goes to x1, x1 goes to x2. Okay, so for me, this is not a braid. So when I say braid, I mean pure braid, okay? So a braid homotopy, right, is going to be some continuous deformation of braids that just only passes through braids, okay? So the strands never cross. So for instance, here we have two homotopic braids, right? I can deform the first and the second just by pulling that strand up, not crossing through any other strands, right? These two braids are not homotopic because if I want to deform this guy to this guy, obviously I sort of have to pass through x2 and x3, right? And this can be shown by computing, say, like linking numbers or something of the first strand with the second and the third, right? Okay, the quote unquote trivial braid is just going to be any braid with k strands such that all of the strands are constant, right? So just I've chosen k constant loops that are all distinct. All right, and because I only really care about these things up to homotopy to some degree, okay? And so I'm going to say a braid is unlinked if it's braid homotopic to the trivial braid. So if I can deform it to the trivial braid without passing any strands through each other. All right, so this is a trivial braid with 3 strands, right? This is an unlinked braid because I can deform it to the trivial braid with 3 strands without passing any strands through each other, right? Okay. If I have a Hamiltonian on my surface, okay, I want to introduce a notion that I'm calling maximally unlinked relative to the Morse range, okay? For me, I'm saying the Morse range because I'm using indices from -1 to 1, okay? Because for me, I'm normalizing the Conley-Zender index such that if I have a C2 small Morse function, then the Conley-Zender index of a maximum is 1, Conley-Zender index of a minimum is -1 on the surface, okay? And so I'm going to say that it's merm or maximally unlinked relative to the Morse range if 1, it is an unlinked braid, okay? 2, every strand of the braid has Conley-Zender index lying inside this Morse range, okay? And 3, it's maximal among all of these conditions, right? So this means that one other way to think about it is to say, if you take some other orbit, some other periodic orbit that has Conley-Zender index inside the Morse range, then it has to link with one of these, right? Okay, link, really, I mean that the braid formed by adding that is not unlinked, okay? This is, in principle, you know, you could have linking number 0 with all of these, and like, just because the linking number is not kind of doesn't totally determine homotonic type of braid, but okay.
Is there an elementary way to show that at least one of these maximally unlinked braids exist? I mean, the Conley-Zender index condition seems non-trivial.
Well, I mean,
but elementary, I'm not using the Floer.
Yeah, I mean, a single strand is unlinked with itself.
Right, but then you have this Conley-Zender condition.
Right, there are you asking, is there an elementary way to see that you always have
Yeah.
something with Conley-Zender index in the range -1 to 1. I mean, I guess Floer theory is, yeah. Maybe, you could probably get something, I don't know, maybe looking at like a hyperbolic orbit, perhaps.
Probably.
If you get index 0 or something.
Yeah,
Um,
I think you maybe if you look at it like this.
Yeah, but okay, I'm happy to assume Floer theory. Since I'm trying to geometrically interpret Floer theory, right? So, okay, and so let me just point out that in principle, sort of yes.
Sorry, so why can't you add just like a constant breaking maximum? What?
I mean, why can't you? Because I guess it's because it's the definition.
There are subsets of the periodic orbits.
And the
Oh,
constant
so
loop is fine.
yeah.
Or it'll be in the graph. It's not like a.
So it just looks at all periodic orbits and then it takes a collection which has.
Yeah, that's it. I'm sort of now I'm trying to study, given a Hamiltonian, I'm trying to study how the periodic orbits somehow determine the Floer complex to some degree, okay? And so let me just point out a few things here. One, it's not clear that something that is maximally unlinked relative to the Morse range is maximally unlinked generally, right? I could have some orbit outside the Morse range that just doesn't link with any of these, right? It will turn out, in fact, that this doesn't happen, but okay,
So basically, I should think of this as some sort of deformation of the case where I take a Morse function.
Yeah.
And all the critical points.
this is exactly what you should think of. That's right, yes. This is somehow your prototypical example is just, if you have a C2 small Morse function, then you just take the critical points and it gives you such a set. Yeah. Okay. And right, and another point is just that it's very unclear what the sort of what the structure of even a merm braid is, right? Like how many orbits there are of things. You don't necessarily have Betty number inequalities if you're not a C2 small Morse function, for instance, on this, right? Okay. Okay, this is just sort of a picture that is meant to kind of illustrate some of these concepts. Okay, so suppose that x1, x2, y and z are in the Morse range and x3 is not, right? So you have some sort of extra rotation around that maximum. Okay, then what are your merm braids? Okay, x1 and x2 give you a merm braid because y1 links with x1 and z links with both x2 and x1, right? Y and x2 are a merm braid because again, y links with x1 and z is links with x2, okay? And so and x3 isn't in there because it's not in the Morse range, right? And just z itself is also a merm braid here, okay? Okay. In fact, it turns out that this is an artificial example and that will never be all of your orbits, but okay. Okay, so now, suppose that you have a Hamiltonian that's not degenerate and you take some J that you can do Floer theory with, okay, is Floer regular. And then theorem that one can prove is, okay, you want to, so this theorem says, take some merm set, okay, so some collection of unlinked orbits that's in the Morse range, is maximally so, and you want to consider now, so now you think in the mapping torus, okay, and you think I have the graphs of these orbits, okay, they form some unlinked braid, and then I want to think of Morse, Floer cylinders that run between these, all of the orbits in X, okay, I only pay attention to things that are running between orbits in X, okay, then it turns out if you essentially, so if I have U in tilde Y J, right? Then of course I can think of U tilde, I can think of its graph, right? In R cross epsilon cross sigma, right? And then these U checks that I'm writing down, right? are just the projection to S1 across sigma of U tilde. Okay, you should think of these U checks that are parametrizing these annuli that are regular leaves of this foliation as coming from the projection of the graphs of your U's.
So in the case where you have a Morse function, they take all the critical points, just saying you look at the flow lines, just lift them up.
That's right.
So that's one, and then that gives you the flow.
That's right. Yes.
And then you continue from that. Okay, this-
Right.
Yeah, and then there's sort of a continuation argument from these sorts of things.
So I guess probably along there, you might have some breaking, if you're not maximally unlinked, you might have some bad breaking.
Yeah, you have to be a little careful about these things.
Presumably this becomes a finite energy collision when we take this about this.
That's right. Yes, that's right. Yeah. Okay. And okay. 1 and 2 are like the main meat. 3 is a consequence of the fact that these are Floer cylinders, or that these annuli are coming from Floer cylinders, right? Which says that the suspended vector field, right, of your isotopy, right, is positively transverse to these regular leaves. Okay, so you know, so here's sort of a rough picture of what these foliations look like in the mapping torus. Okay, if you're maybe like on the disk, or maybe you think you collapse that boundary down, you have the sphere, for instance. Okay, you have these 3 orbits, and you have Floer cylinders that sort of are running between them and then running down to the boundary, which maybe you think of as another critical point, okay, or another periodic orbit, right? And you should think of, and then somehow the positive transversality is saying, you know, the suspended vector field is sort of always pointing in the consistent positive direction. Okay, it always intersects these leaves in the positive direction.
Could you explain the points again? What are these points?
So these points are, say, your merm braid. You should maybe think that you're on the sphere, just to avoid thinking about the boundary. You should sort of maybe collapse that down, the boundary down to a point, and think maybe you're on the sphere, right? And then these are all, you have sort of these index 1 leaves, right? So maybe this is sort of an index. CZ index 1, index 1, index 0, and the south pole is index -1. Okay, and then these come in sort of 1 parameter families, and you sort of, it's the usual kind of Hofer-Wysocki's ender kind of picture of these things.
So just 2, 3, 4, 3 to 3 flames, whatever.
Yeah, yeah. I mean, these is sort of, yeah.
I realize that as a particular example. What are you doing?
I not in like an easy way in some sense, right? Because somehow, you know, it's like, this is one of these things where it's like the contact versus the Hamiltonian setting are kind of like at opposite ends of the integrability spectrum. So it's like somehow, yes, this is morally true, but you know, I don't have a way to like see this actually as arising as one of these like 3-2-3 things, you know, foliations.
But S1, okay,
Yeah.
The S1 cross S2, you can think of the S2 like something.
Yeah, I mean, yeah, maybe that's it. I haven't thought about trying to
So
realize it in such a
for
way.
the case of the orbits with index 1, index -1, there's 1-dimensional family of orbits. Why these different ones don't, like, their images are destroyed?
Yeah, that's part of the theorem.
Okay.
Yeah. It's part of the theorem. So, you know, since it's looking increasingly likely that we'll get to like the real proof part of it, I'll say something about it, which is that so there's sort of an obstructive part of the theory, and then there's sort of a constructive part of the theory. The obstructive part of the theory tells you something about how the topology of collections of Floer type cylinders behave inside of R cross S1 cross sigma, or in you can, and you know, with some work one can understand their projections as well. Okay, and roughly speaking, one has 2 important ingredients. One is sort of the asymptotic analysis of Hofer-Wysocki's ender plus some later adaptations by Richard Seifring, which kind of tell you how the structure of the braid. So okay, I mean, I guess I should just, as I'm saying it, I should write this stuff down here. Okay, so sort of imagine doing R cross S1 cross sigma. Okay, and Okay, if this is R. And then just imagine that the other. That's what sigma, okay? So you have a given orbit at say negative infinity and an orbit at positive infinity, okay? Maybe X or Y, for instance. And so, you know, you have some Floer cylinders kind of coming out of X, for instance, okay? And this asymptotic analysis tells you, roughly speaking, that if you look very close at negative infinity, what you see is a braid near X, okay? And it tells you also how the topology of that braid is related to the Conley center index of X, okay? And similarly, when things go into Y, you get a similar picture at the positive asymptotics, okay? And then what you do is you also, so you have some picture sort of a braid, what the sort of braid formed by like U, say you have like U1 near minus infinity and like U2 near minus infinity and U3 near minus infinity or something. So you have some collection braids like that. Call that maybe like X minus infinity. So this is some braid, right? And it goes to some braid near plus infinity, and you need to control how things kind of evolve, right? And you control that through sort of positivity of intersections arguments, okay? And it turns out that the fact that you are running between sort of maximally unlinked things allows you, with control over the Conley center index, allows you to conclude that in fact so they cannot self-intersect. Not or first the projections can't self-intersect, and second they can't intersect each other. Okay.
The unlinked or the maximally unlinked condition gives you compactness in the node, where you don't have any breaking.
So could you elaborate a little more on why maximally unlinked means that the leaves of the foliation are disjoint? Is the idea that if I look at the linking of the negative ends and I have two leaves that intersect, then the linking of the positive ends is at least one greater? And that's why
Yeah,
it's
so
something-
because you're in the Morse range, things come out unlinked, okay? Fact.
Okay.
Also things go in unlinked, okay? If they did intersect, it turns out positivity of intersections corresponds to linking number increases, but linking number cannot increase because they need to go in unlinked.
Sounds
Okay.
good.
Yeah. Another question? All good? Okay. So yeah, a few additional remarks. Okay, so just to kind of review here, what this gives you is if you have some merm braid, right? What this gives you is sort of a geometric understanding of the Floer cylinders that run between the strands in the merm braid. Okay. Reasonable question is, if I have two orbits inside the merm range, can I necessarily see every Floer cylinder that runs between these things? The answer is yes. Okay. It turns out that if you have a non-empty moduli space, then in fact these two orbits are unlinked, and so they are in some merm set. Okay. And so what this tells you is that if you vary the merm braids, right, then you see all of your Floer cylinders inside this range, all of the Floer cylinders that are sort of needed to define the differential between degree 1 and 0 and 0 and -1. Okay.
So basically the argument is like if you see another cylinder with asymptotics in your points that you
Yeah.
set out.
Yeah.
So see from the intersection theory just tells you okay, it has to be one of the curves in foliation, otherwise you would have to set a positivity.
Yeah. Yeah. Yeah, you can think of it like that, for sure. Okay, and so in principle, this should allow you to dynamically characterize spectral invariants in sort of middle degree, right? Because you have all of the information necessary to understand your Floer complex there. There's some sort of quotient, and you should be able to do this essentially by understanding something about kind of the combinatorics of merm braids, right? As they kind of relate to each other, because if you take two merm braids, right, they may have some overlapping periodic orbits within them, right? And so they're going to share some Floer cylinders running between them. But okay, if you can kind of quotient out by that, you should be able to completely understand what these spectral variants are.
Sorry,
yeah.
I have another question.
That's all right.
If you have two X and Y with a
Mhm,
non-trivial moduli space of that,
mhm.
is a element of that moduli space always going to be in leaf of the foliation
Yes.
FX?
Okay.
So I guess, yeah, my question is something of completeness or something, like when you take some merm braid X
Yeah.
and construct the foliation.
Yeah.
Like all of the possible moduli spaces between.
Yeah. Between those things are
Between
seen.
things will be
Yes.
inside the foliation.
That's right.
I guess this is I mean, the reason I'm asking this is maybe it's a little too subtle to bother or something, but it could be that you have a foliation, but with some X and Y that have a non-trivial moduli space, but then the moduli space is not represented in that foliation.
Yeah, that doesn't happen.
Okay.
Yeah.
Because you have the foliation.
It'll break on these things and,
Oh, okay. Yeah.
because then you'd have gluing and you could, yeah. Yeah, so, okay, I mean, I haven't sat down to seriously think about this question of characterizing these middle dimensional spectral invariants, but, I think it should be feasible, it should be probable, right? Happy to talk about it with anyone who's interested, okay? And now let me explain how you can use these things to construct particularly nice Calvez type foliations on your, okay? So these are foliations, I've just described how to get foliations from Floer theory of your mapping torus, right? And now we want sort of singular foliations on your surface, okay? That are positively transverse to or homotopically positively transverse. In fact, we're going to do better, okay? So the idea here is that you have this foliation of your moduli space by annuli, okay, and loops, okay, they're your singular orbits, right, the braid. And okay, annuli are themselves foliated by circles, right, in a sort of canonical way. These are just one parameter families of circles, okay. And so what you actually get is a foliation of your mapping torus by circles, right? And so you can just slide along these circles, okay? This gives you a loop of diffeomorphisms, all right? And okay, call that diffeomorphism psi of X, right? And okay, this, if you can think of, if you sort of slice this foliation over any t in your circle, right? Then this gives you a foliation of your surface, right? Because these this foliation fx is sort of always transverse to the vertical fibers, okay? And so this sliding diffeomorphism is precisely a diffeomorphism, or is a diffeomorphism that sort of sends this foliation over 0 to the foliation over t, right? Just sliding.
Wait, question, sorry.
Yeah.
I thought you were just looking at S1 cross sigma, but you're actually looking at mapping torus, or
S1 cross sigma.
like there's a diffeomorphism.
S1, I'm thinking, so because for me, so S1 cross sigma, yes. This is a terminological thing. Because it's isotopic to the identity, I'm just sort of,
Oh, it's S1.
Yeah. I should say all of this can be done in a twisted way if you want to deal with things that are non-isotopic to the identity, right? But okay. Okay, here, this is just some picture that's supposed to give you some idea of what this sliding diffeomorphism does along a given leaf, okay? I have a point at 0p, right, at the fiber over 0, and it passes through sort of a unique U, U00, and I slide it along to T U0T, okay? You can think of it as, integrating the vector field to by sort of delta U of these foliations, right? And so interesting fact here is that so first of all, it turns out that these foliations, these singular foliations over the surface, right? Maybe I should give a picture here. The idea here is in this picture here, okay? Here you have your foliation of the mapping torus, okay? Here you have the slice over 0, okay? And so when you look at the slice over zero, what you get is this singular foliation of your surface, okay? And it turns out that this sliding foliation that I described, if you compose by the inverse of it, so you run your isotopy and then you slide back along these circles, okay? This gives you a new isotopy, right? And new isotopies has the same time one map because this is the loop of diffeomorphisms, right? In fact, it's contractible loop of diffeomorphisms. So you don't even change the homotopy type rel endpoints if you're on the sphere, okay? And it turns out that that isotopy is always transverse to this foliation at the slice over zero, okay? So you get something that's even stronger than sort of this homotopically transverse condition that Calvez gives you, right? You get a genuine, you get an isotopy that is genuinely transverse to this foliation.
And it's global.
And it's global,
So
exactly.
does this follow from that? Does this follow from that third point you wrote, where the foliation on the R cross mapping torus is transverse to XH?
Yeah, basically right, yeah. And yeah, then just some computation, yeah. And let me just say that you also get that this foliation, this Calvez type foliation on your surface is actually a morph type foliation, right? Okay, that is to say that there is a smooth function, okay, whose critical points will correspond with the correct indices to these singular points, and the foliation that you get is a pseudo gradient flow for this a negative pseudo gradient flow for this for that Morse function. Okay, so in particular, that tells you that the structure of merm braids, right? If you have a given merm braid, it turns out that actually it has the same sort of structure of critical points with indices as a Morse function has critical points. Okay. Which again, sort of a priori, no reason that should be the case.
Maybe not, but like, is there like a homological reason why you have that? I mean, you have it for the more space, right?
Yeah, well, I mean, ultimately, this is a homological reason. Yeah. So, I mean, like, yeah, probably there's some sort of argument one can run about doing.
Basically, practice as you sort of pointed out, right?
Yeah.
Just to run the deformation and then you understand how to break it and all.
Yeah. So I guess, yeah, maybe it's that it's not that there's no reason, but it's that if you gave a reason, it would, you know, ultimately give you this kind of these sorts of foliations, right? Okay, and right, so I should also say that these sorts of foliations, right, particularly in the case of the disk, were originally studied by Barney Bramham, and to sort of considerable effect. He sort of used them to study sort of irrational pseudo-rotations on the disk, okay, and find sort of conjugates of rotations that C0 approximated them in various ways, okay? And he actually does it by looking at kind of these sorts of foliations in some sense that arise as iterates of them, okay? Now, of course, you would actually need to leave the merm range to do that. But okay, he constructs these things by hand, and so that's sort of not a problem for him. And a question that kind of ends up showing up in this question of whether these approximations, these conjugates, conjugates of rotations that approximate your periodic, your irrational pseudo-rotation are integrable, right? Ends up being equivalent to sort of asking if these sliding maps are Hamiltonian, okay? Or sort of for suitable T's, okay? And it turns out one can show that in fact these sliding maps are Hamiltonian. So remember, I told you that these were diffeomorphisms, right? These loops were diffeomorphisms. Turns out that they're Hamiltonian if and only if the associated isotopy that you get on the surface is a Hofer geodesic. Okay, so somehow your Floer cylinders tell you how to straighten out your isotopy in such a way as it's somehow very close to optimal, if it, if they're Hamiltonian, and the defect from being Hamiltonian somehow is measuring how far away from being a Hofer geodesic your resulting isotopy is. Okay.
I might just, I'm probably just missing something, but the sliding map is, the loop is, it's area preserving already?
No, you don't know it's area preserving.
Oh.
No, yeah.
Weird.
Yeah. And in fact, yeah, I think you could probably get it to be, say, like it's symplectic if and only if the isotopy is.
So wait, so how do you show that it's area? Or I guess I'm just asking, how do you prove this?
Yeah, maybe we can save for questions. Yeah. Okay. Yeah. Okay. And so I think an interesting question that I haven't thought deeply about, but I think is interesting, is to ask what Hofer geodesics can be realized in this manner, right? So if I give you a Hofer geodesic, can you sort of find conditions on, a merm braid such that like this actually arises as the resulting isotopy, right? I guess one other thing I should say, just going back, is that of course one knows that there are, for instance, on the sphere, Hamiltonian diffeomorphisms that are not reached by any Hofer geodesic, right? So that gives you sort of an obstruction. There's an in-principle obstruction to making this this loop Hamiltonian, right? It's not always possible, but when it is possible, sort of can you construct a foliation that sort of does the job, right? And there's, morally speaking, okay, and I can't substantiate this in a serious way, but I would say that somehow this isotopy that you get after composing by the inverse of the sliding map seems to kind of want to be as close to integrable as possible. Okay, but okay, this is just hand waving. I mean, like when it can be a Hofer geodesic, it roughly behaves like, you have this sort of positive transversality condition, so that you're behaving quite like an integrable system, except, okay, in principle orbits can cross, but, okay, that it turns out that when that happens, you get entropy. So if you knew that you had no entropy, then, these things behave quite close to integrable systems. Yeah, there's sort of some general way in which the Floer theory kind of tells you how to straighten things out in a way that behaves quite nicely, let's just say. Okay.
Maybe just a general question.
Yeah.
Are there no known examples of like maps like that have what am I saying? Non-integrable but still zero entropy?
Yeah, I mean, irrational pseudo rotation.
Right, exactly.
Or
Yeah, those.
such things. Yeah, I
I
think the question is sort of whether, I think the question a lot of folks are interested in is something like, if they're if they have zero entropy, and for instance, like are, I don't know, not like weakly mixing or something like this, so like the obvious obstructions to integrability vanish, can they be C0 approximated by integrable systems? Okay. And I think Barney showed us somehow how to use Floer theory to answer that question in at least some cases. Okay, and using these sorts of foliation. Whether you can sort of try to do that in general and develop a general strategy for it, I don't know, but I think that if you're trying to do that, this is maybe the only set of tools that we have that could attack that kind of questions.
So,
yeah.
Can you improve Barney's theorem to Hofer approximation? I guess he does C0 approximation.
I haven't thought about that. I don't know. Yeah, I could.
That would be pretty good.
Couldn't tell you. Yeah. Okay, so I want to move on somewhat quickly, I guess, to the sort of second set of results that I promised you, where we're going to kind of characterize certain fundamental classes dynamically. Okay, certain or certain chains that represent the fundamental class dynamically, okay? So there is this thing called a PSS isomorphism, right? There's an isomorphism in general, sort of between the quantum homology of a closed symplectic manifold and the Floer homology, okay? And the rough construction, so it's not particularly important, but perhaps the details aren't all that important, but it's induced by some chain level map, okay? Roughly speaking, what one does is you sort of you look at disks that sort of, you fix some Morse function, you fix some Morse function, some Morse small pair FG, okay? And you should think of maybe the manifold M sort of sitting over this for 0, somehow U2 cross M. And what you want to do is sort of count certain disks that satisfy a perturbed Hamiltonian equation that's sort of 0 near the origin of the disk, okay, and agree with the usual Floer equation, the positive end, and you to see where some point in the Morse complex. So you look at sort of the Morse complex associated with F and G, and to see where some point goes. What you do is you do some count of these holomorphic or perturbed holomorphic disks that pass through the unstable manifold of P at the origin. Okay, and then you look at the orbits that they're possibly asymptotic to, and you do sort of the usual count of these things, and this gives you some chain in the Floer complex. Okay, and okay, so that requires that you sort of define some data, some what I call regular PSS data, which is your Morse male pair plus sort of this perturbed Floer equation data, right? This H and sort of Cal H and J here, okay? And when you have, so given such regular data, you can define a map at the chain level, okay, that sort of counts these disks. And okay, you can then use this to give a definition of sort of a different kind of spectral invariant than the usual Schwarz spectral invariant, okay, that essentially looks at, so I fix a homology class, a quantum homology class, okay, and I don't look at the minimal level at which that quantum homology class appears in my chain complex. Instead, what I look at is the minimal action level at which such a chain representing that is hit by some PSS map. Okay, so you think somehow you're thinking of probing the Floer complex by these PSS maps. Okay, and somehow one should think of these as like continuation maps from the 0 function. Okay, and okay, it turns out that this gives you a well-defined spectral invariant. Okay, it's independent of J, and it has almost all of the usual formal properties that one expects. Okay, the only sort of difference from the usual list of properties is that you don't necessarily have the triangle inequality. What you have is the weak triangle, what I'm calling the weak triangle inequality, where, okay, essentially it's the triangle inequality where one of the homology classes is the fundamental class. Okay, so the upshot of this is that since we normally deal with spectral invariance through these formal properties, most of the proofs that one normally gives for say the Schwarz spectral invariance, so long as you don't, really need to take a triangle inequality where one of the classes is not the fundamental class, you can just run those proofs and they're true for these PSS image spectral invariants. Okay, so for instance, this defines a symplectically invariant norm on Ham, right? Say Fedini's proof of like C0 continuity of this for surfaces goes through, various kinds of usual proofs that one would run for these things go through. Okay.
What extra things is it capturing?
What extra things is it capturing?
Why looking at
Yeah, so why should we look at these? Perfect question. Yes, good. Why? So it's somehow I've given you a somewhat inferior, a somewhat inferior spectral invariant, and like, why do that, right? Why do that yourself? Well, the answer is that I can actually compute that thing, okay, dynamically. Let me just say this, which is, it's an open question as to whether this actually agrees with the O-Schwarz spectral invariant or not, okay? Somehow there are good philosophical reasons to believe that they shouldn't be equal, okay? Because somehow, like I said, one can think of the PSS image spectral invariant as probing via continuation maps from zero, okay? Whereas if you sort of read O's work on sort of chain level geometry of these things, you can see that the O-Schwarz spectral invariant is basically can be understood as a spectral invariant that arises when you allow kind of probing by continuation maps that are kind of arbitrarily small. Okay, so somehow this is probing from long things, sort of long continuation maps, versus using all possible continuation maps. Okay, but actually showing that they're different is tricky because I mean you'd actually need some way to compute the O-Schwarz spectral invariant such that it doesn't agree with the PSS image spectral invariant, but then you need some way to compute the O-Schwarz spectral invariant that doesn't just use all of the list of properties that the PSS image spectral invariant also uses, right? So you sort of need to get beyond sort of just the formal approach, right, in order to sort of answer this question. So I think it's an interesting question. It's tricky, okay? Okay, and last remark on that is that in the autonomous case, at least if you're not on the sphere, then there's work of Emilia Bedini that implies that at least when your Hamiltonian is autonomous, not necessarily C2 small, but autonomous, okay, then these two spectral invariants coincide. Okay, so that means that if you want to find counterexamples, you need to get somewhat far from integrable systems. Okay. Okay, and now to answer Luia's question, why care about these PSS image spectral invariants? Let me give this topological characterization of the PSS image spectral invariants. Okay, so to give that, I need this definition here. We're going to say that a braid is positive, okay, if I can choose cappings of these braids, such that the disks of these cappings intersect only positively, and transverse. Okay. So I should also say that if this braid is unlinked, right, then there are no intersections, and so trivially that's also a positive braid, right? So an unlinked braid is a positive braid under my definition. Okay. I should remark that this is not the usual notion of a positive braid, right, used by braid theorists. Okay, that's sort of given in terms of positive. You can be written as sort of a product of positive generators. Okay. Because strictly speaking, this is a definition of positively inverted capped braids, but I've avoided talking about cappings this whole time. So, okay. But in the paper, this is sort of done properly. Okay. And so, okay, once I have this notion of a positive braid, a positive capped braid perhaps, then I can give you a characterization of which Floer chains, okay, represent the fundamental class and are hit by some PSS image spectral. By some chain level PSS, okay? And so the characterization is the following. If I have a braid, I'm going to say it's maximally positive relative index 1. If every orbit in the braid has index 1, okay, it's a positive braid and it's maximal subject to these two conditions, okay? That is, if I add any other index 1 orbit, then I no longer have a maximal, a positive braid, and braid positive when I add an index 1 orbit, okay? And it turns out that these are precisely the things that represent the fundamental class via the PSS map, okay?
So what is this notation of PSS map start D?
That's some regular PSS data. It's a chain level map, and so to define the chain level map, you need some generic source of data. And so this statement says that if you have some maximal positive braid relative index 1, then in fact you can find some chain level data such that that is such a,
So the chain level element might operate dependent on D, but not the whole space.
yeah, exactly. As you change D, you'll hit different maximally positive index, rel index 1 braids, but yeah, they all represent fundamental class.
So if O Schwartz is equal to PSS image, then essentially every homologically non-trivial, every Floer chain is a positive braid. Is that
No,
what this is, or-
no, because it's a statement about the peak action level,
Oh,
right? So there are,
yeah.
that's it. I will say, there are things that represent the fundamental class that are not such that are not maximum positive rel index 1, but okay, the question is whether the peaks of these things coincide when you do this sort of min-max that defines the spectral invariance. Yeah. Okay, and so corollary is that, okay, and this is why one is maybe interested in using these PSS image spectral invariants rather than the Schwartz ones, is that you actually have sort of a dynamical interpretation of this of these spectral invariants, right? And okay, this gives you a dynamical interpretation of, for instance, the associated spectral norm. I should say that recently there's work that's been announced as sort of forthcoming by Myvis, Alvis, and Byung-Jun. I can't remember his last name. Choi, thank you. Who? Song.
Yeah.
Thank you. Yeah. Okay. So there's work forthcoming that shows, for instance, that topological entropy is like lower semi-continuous with respect to this spectral invariant, and it turns out the proof really actually needs these spectral invariants and can't be made to work for like the O-Schwartz spectral invariants, for instance, which is a bit odd. They have it for the Hofer norm. Yeah. And that, for instance, it also implies like C0, anyway, but yeah. So just to say that somehow, it's, it turns out, yeah, the spectral invariants are useful in some way or another, right? Yeah. And, okay, right, and so, okay, let me, I'm wrapping up, I see I'm over time here, so I'll just.
Well, plus X minutes for technical incompetence.
Okay, great. In that case, I think we can get through it. Okay, so I think a very interesting question here is, okay, so I've given this notion of a positive capped braid, which I've told you then does not coincide with the usual notion of a positive braid given by braid theorists, right? And I think it would be very interesting to be able to give a characterization in usual braid theoretic terms, okay? That is in terms of the corresponding word in braid group, right? Because if you could do this, then you could start doing you could start algorithmically kind of computing these and numerically approximating these spectral invariants sort of computationally, right? Which dynamicists would be rather interested in understanding, okay? And okay, so finally, let me just say a little more about the general theory that underpins these results and how you kind of get them, okay? So like I said, there's sort of an obstructive theory and a constructive theory, okay? And I've sort of briefly described this obstructive theory, right? So the idea is you think of your cylinders giving you graphs in R cross S1 cross sigma, right? And you think of those graphs as giving you deformations of braids from the negative end to the positive end, okay? But actually, somehow you shouldn't think of them precisely as giving you deformations of braids from the negative end to the positive end, because you can have multiple things going in and multiple things, multiple things coming out and multiple things going in. So you really want to cut sort of close to positive and negative infinity and look at the resulting asymptotic braids, where the Hofer-Wissot-Zender kind of asymptotic theory gives you control over the structure of these braids near near the orbits, right, asymptotically. And then you know that, so Gromov's trick tells you that the graphs can be interpreted as pseudo-holomorphic cylinders. So you have positivity intersections of these things. Positivity intersections then turns into a monotonicity, a facto monotonicity of linking numbers. Okay, you can define linking numbers on surfaces in general for sort of capped braids. And okay, then this gives you a very good understanding of sort of how the sort of obstructive theory for how Floer type cylinders can, collections of Floer type cylinders can sort of exist inside the symplectization of the mapping torus, okay? Then, and so that gives you kind of good understanding of sort of what would have to be true if certain cylinders existed, but then you need a constructive theory, okay? So something that says essentially that if all of the sort of obstructive theory kind of tells you that things could exist, then you need to show that actually they do exist, okay? And okay, you sort of build this by hand. It turns out that at least for continuation type cylinders, you can sort of do this where you sort of find suitable smooth collections of cylinders, and you sort of perturb them and adjust them so that you can make them appropriate solutions to some continuation type data. Okay, and in fact, you need them to be regular continuation type data, and okay, you can do this. And then once you do that, this gives you a pretty good understanding of sort of the index one cylinders that exist, and define your continuation maps, okay? And you can then use this to kind of pull information from systems that you understand to the system that you're studying, okay? And these foliations, they follow by sort of applying this scheme to suitable small Morse functions, right? So you essentially pull the transverse foliation from your Morse function to the system that you're studying, okay? And you get a transverse foliation there. That's how you get your foliations there. And characterizing the PSS level, chain level maps basically follow from, applying the scheme to continuation maps from the zero Hamiltonian. Okay, you think of the PSS map, the chain level PSS maps as being kind of continuations from the zero Hamiltonian. And you do this kind of scheme. Okay. That's it. Thanks, guys.
You're the
Yeah, so
Yeah.
we can let people go and yeah, some more later. Oh, you want to say something?
Well, not be too long of a question. Well, so in this theorem you wrote about the sliding maps are a Hamiltonian
Yeah.
curve if and only if it's Hofer geodesic.
Yeah.
I guess, do you also show that the sliding maps are always area preserving, or
No,
is-
I mean, they're not
yeah,
always area
they're,
preserved.
okay, oh, they're just not always area.
No, they're not.
Yeah,
Yeah.
okay. Is there a good example of when they're not area preserving?
Yeah, if you take Hamiltonian where the time one map is not reachable by a Hofer geodesic, then they simply can't be. I also
Well, they could be area preserving, but not Hamiltonian.
I see. No, because they're on a sphere.
Oh, this is a theorem on the sphere.
Yeah.
Oh, okay.
All
right.
Yeah. There are also obstructions that you can get in terms of kind of like spectral invariants. These are a bit harder where you can, there are other obstructions that I could give you, but are sort of harder to state.
No, I
But,
mean, it would be very surprising if they were always area preserving.
Yeah.
It's just some foliation.
Yes.
Yeah.
It's yeah, I mean, I think there's an interesting question where you sort of, if you fix your merm braid and you sort of vary J, right? Then this corresponds to sort of like varying the corresponding foliation, right? And I think there's sort of an interesting question as to can you can turn this into sort of a variational problem in terms of how much you're deforming areas, right? So somehow that how much this corresponding loop deforms areas. And you can, I think it's an interesting question to ask, can you find optimal J's such that the corresponding map is sort of minimally area deforming, right? It's tricky though, because this involves sort of studying kind of the second derivative of the Floer operator in like a really serious way.
Yeah, I mean, the main issue with extending Barney's theorem from C0 approximation to Hofer continuation is this issue that these sliding maps are not necessarily area preserving.
Exactly.
If that can be handled, then I think the theorem's not so bad.
No, it's tricky. That's it. That's why I think an interesting way to approach that is sort of trying to attack like the converse direction, right? Like if I have a Hofer geodesic, when can I realize it in this kind of way, right? Like when can I, because you know, if you have a Hofer geodesic, then okay, you can kind of try to make this like a maximal isotopy, right? And then try to find a loop of diffeomorphisms that turns these things into Floer cylinders for some J, right? And that would, you know, force you know, that would force that loop to be a Hamiltonian loop, for instance, right? By that theory. Okay. Sorry, this is getting into the weeds.
Okay, let's thank Dustin again.